Okay, hello everybody to this week's ISGC seminar talk. Today's speaker is Bum-Hoon. He got his PhD in 1989 from the Columbia University. He was a professor, first associate professor, then full professor from 1996 to 2022 at the Department of Physics at Sogang University, where he is still now also a professor emeritus. Then from 2005 to 2020, he was the director of the Center for Quantum Spacetime, where he still remains as a researcher. And since this year, he is also an adjunct professor at the Department of Physics of Shanghai University. Thank you very much for agreeing to give this talk. The stage is yours.
Okay, thanks for the good introduction. So I'm happy to have a chance to present through this intercontinental seminar. The topic that I'd like to share with you is about the dilaton-Einstein-Gauss-Bonnet gravity and also the cosmology implication. So the way I'd like to present is, first, I'd like to give some short motivation why we should go gravity theory beyond Einstein. Because Einstein gravity seems to work perfectly, but then why should we go the theory beyond Einstein? Now, so as a simplest example of the theory beyond Einstein, I'd like to introduce you adding some higher curvature term, Gauss-Bonnet term. So then I'll just try to introduce the property of this the gravity theory with Gauss-Bonnet term as a gravity theory itself through the black hole solution. Then next, what is the cosmology that such a model will present? Then I'll summarize. Okay, as a motivation, the question is whether we do need any theory beyond Einstein, whether it is needed. I'd like to approach from two aspects. One is a theoretical aspect, another is observational aspect. From the theoretical point of view, as we all know, through the development of the field theory in 20th century, later 20th century, now we believe that every theory should be understood as effective theory. So then, according to that, in principle, we are going to have as a power series of the curvature scalar. Then we in addition to the linear term, we may have quadratic terms and the highers. So, for example, actually, people thought about many people believe that the string theory may be some UV completion of gravity theory. Then people explicitly calculated the higher order terms when we go when the energy is getting lower and lower. In other words, as a supergravity, let's say. Then they actually showed that higher order corrections is not zero. It's there. So in other words, you may say that Einstein gravity theory, which is the simplest one as a linear theory in the curvature, is a simple. However, it is incomplete as of the field theory, as we know. So in principle, if you accept that effective theory aspects, then there must be higher orders of curvature terms in the gravity theory. The only question is whether they have some large enough to have some observational effect, or let's say whether we have a precise measurement to see such effects. Another theoretical aspect is just bypassing holography. So through the ADS geometry asymptotically, that is believed to be equivalent to the one-dimension lower quantum field theory. In such case, a black hole should be understood as a thermal system. Now, as for the observational aspects, I will not go into detail here. However, at least for the expansion speed Hubble parameter, if you take a look at this one before 2013 or something, you may see that the red color, which is based on the direct observation based on the supernova, and the blue color observation based on the CMB. So in other words, a long time before, and the local distance quite close to us, then you may see that they are consistent. However, as time goes on, at this moment, definitely they are not, there's some discrepancy up to close to the 6 sigma. So at least, so we are not saying that the cosmology based on the Einstein gravity, or in other words, lambda CDM is wrong, but actually it is really challenging some observation. So there are some such observations. So question is whether we do need any theory alternative to lambda CDM. Now, then let's move on to the gravity theory with Gauss-Bonnet term. So the basic idea is that, so just like Einstein theory, let's stick to the metric only, no other methods. And also let's require that the equation of motion is a second order. So if it is not, then we have many problems, such as unphysical degree freedom. So many in many different guises it will appear. With these two requirements, then the general Lagrangian was written by Lovelock. And so to be more explicit, in the 4-dimension case, then we have two terms, so-called L1 and the L2. In other words, there is a linear term in curvature scalar and a quadratic term in the curvatures, which is some special combination of scalar and also Riemann tensor. Also here we have a Ricci tensor. So some special combination, which is called Gauss-Bonnet term. However, in the case of 4-dimension, this Gauss-Bonnet term is well known to be boundary term or it's a topological term. So this one does not contribute to the equations of motion. So we are back to Einstein gravity theory. So the theorem, the Lovelock's theorem is that in 4-dimension case, if we require the second order equation of motion and also only metric, using metric, then Einstein gravity is the only theory. So that's very tantalizing because we gave a motivation to go. There is some enough reasons to go behind Einstein. However, this theorem blocks going beyond Einstein. So what should we do? Essentially, to go beyond Einstein gravity, essentially we do need to introduce some new degree of freedom. Okay, so the new degree of freedom can be in terms of really some fields, like a scalar fields or any vector fields or particles with some spins, or in terms of higher curvatures. So higher curvatures, in a sense, adding quadratic terms like a longitude. So changing the massless graviton to the massive graviton, and the longitudinal degrees are like scalars. So it's, in a sense, it's somewhat similar to the case of introducing scalar fields. Okay, so with that in mind, so let's just stick to the simplest case, in other words, quadratic terms. If the dimension is higher than 4, we can write down the quadratic term as Ricci scalar or Ricci tensor or Riemann tensor, as all may be independent. However, if they are independent, then we are ending up to so each one has 2 derivatives, so usually they have 4 derivatives, so we are ending up to 4th order equations of motion. So that's not what we want. So by imposing second order, then the conclusion is that only when these scalars and tensors are combined into so-called Gauss-Bonnet term, then we are given some second-order differential equation. So that is essentially Einstein-Gauss-Bonnet theory. So here, Einstein term and the Gauss-Bonnet term. Now, we live in the 4 dimension, but in the case of 4 dimension, as we said, the Gauss-Bonnet term is topological or boundary term, so it's non-dynamical. So what should we do? In such case, to make that term some dynamical, rather than constant here, like the higher dimension, constant coupling, we have to introduce some functional dependence. So it's a coupling function rather than coupling constant. So typically, we may choose this coupling function is, in a sense, infinitely many parameters. So it's too complicated in general. There are some reasons, like from string theory, that this may be essentially given in terms of exponential, or for many other reasons, or maybe we may take the simplest monomial terms. By this, the function can be reduced to 1 or 2 parameters, depending on how you give the functional form. Okay, now let's move on. Since that is the one, this one is called, here we have a dilaton field phi, and also Einstein term and the Gauss-Bonnet. So we call it as a dilaton-Einstein-Gauss-Bonnet gravity. So now let's think about the property of that, and especially let's think about the black hole solution. So we are given action. Red colors are the additional terms compared to the Einstein term. Then in the equations of motion, there are some more contributions in the Einstein equation, and also scalar field equation also in addition. Here, the energy momentum tensor Gauss-Bonnet is actually some in terms of the curvatures, but rather than putting this into the left-hand side, we moved all the coupling function dependent one to the right-hand side to interpret Gauss-Bonnet term as some new kind of method. So that's the kind of method. Okay, so here I will not go very detailed. The only thing is that by rescaling, alpha magnitude is not important, but sign is important. And also the sign of this, when we choose this exponential form, sign of this gamma, if you reflect a sign, then by reflecting phi sign, so you can choose only one sign. So there is such property, but let's not go for the detail. Now, so it is. I don't know anybody who got the analytical solution in this case. So everything should be numerically done. So here is the is a dEGB black hole solution for some given parameters. First, a scalar field solution gives asymptotically going to 0, but near the horizon they are not 0. So here. So that means we may call this as hair. So it is inevitable that every black hole has hair. However, this hair is not independent, but once we give the mass of the black hole, these hairs structures will be determined. In other words, they are secondary charge rather than primary charge. Also, there is a metric component. So numerically, it clearly shows that the black hole solution exists. What is interesting is, so unlike the Schwarzschild case here, where I drew here the horizon size and also mass of the black hole, then we do know that that's a linear relation. So we drew here again. Here is a 0 is here. So this straight line is a Schwarzschild black hole solution. You may just take a look at this upper part, because lower part is the scalar field here. So only if you take a look at the upper part, if gamma equal to 0, that's the in the exponential form, e to the gamma phi and the gamma equals 0, then it's a constant, so it does not contribute, so it's an Einstein gravity case. So in other words, gamma equals 0, Einstein gravity case, any size of black holes in principle can exist, like in the primordial black holes. And always mass will be proportional to the charge. However, once you turn on Gauss-Bonnet term, they stop somewhere. So let's look at the gamma equals square root 2. And then asymptotically, all the black holes exist, but stops here. If gamma is becoming smaller, it comes more smaller black hole, then stop there. And have so there is exists a gamma, much smaller black hole exists, but eventually there cannot be smaller than some critical value, or there cannot be black hole mass smaller than the minimum mass. So it's like that. So it's a black line is gamma equal to 1/6. So they come down much lower. So however, still there cannot be black hole smaller than some critical size, minimum size, or there cannot be black hole with a mass smaller than this minimum mass. Only when gamma goes to 0, this the minimum mass or minimum size will become smaller and smaller and go to the limit of the usual Schwarzschild black hole case. Interesting thing is that the minimum mass in the usually positive case, if we are further off from the Einstein, in other words, if gamma is bigger, we may say that the theory is getting more and more off from the Einstein. Or in other words, Gauss-Bonnet term is becoming more and more important, contributing more. In such case, the minimum mass increases. So in other words, there cannot be some small the light black hole. That minimum mass is quite large. So you may interpret that as, in a sense, the quadratic term with a Gauss-Bonnet, that's a kind of repelling. Of course, gravity is attractive. However, they are making the attractive property much weaker. So remember, if you have always collapsing of the black hole occurs, if they can overcome any resistance, so in that the spirit, we may say that this is less attractive, so that the two small size black holes, they cannot really shrink it to the black hole. In the alpha negative case, it's more interesting. Gamma minimum increases and decreases. So question is, what is the role of this minimum mass? Does it mean that the new phase, in other words, if we think about any mass, only the mass larger than the minimum mass, they are black holes. But what if we have some object whose mass is smaller than that? Is it solitonic star? There are some studies, but still I'm not sure whether we really understand the full content. Okay, another thing, so let me, due to the time, let me just be very quick here. So we do know that if we have two black holes, they will merge into one. We observed already that such phenomena through so they are merging and releasing some gravitational waves form some of the energy. Question is, if they are somewhat fundamental, can we imagine something like the inverse process? In other words, a single black hole splitting into two. Of course, this process is not occurring in the Einstein gravity case. So, for example, if we think about the Schwarzschild black hole, the argument is based on the entropy. If we compare the final, so if they are fragmented into two, final two black holes entropy and the initial single black hole's entropy is really comparing the horizon area, then always is smaller than 1. So in other words, the initial has more entropy, so it's preferred. However, if you just pay attention to this equality holds when delta goes to 0. So the splitting is in terms of delta and the 1 minus delta. So delta goes to 0 means they are shooting off infinitesimal mass with of a black hole. So black hole with a very tiny infinitesimal mass, then it will not essentially change any horizon area or any entropy. So we may say that the Einstein gravity is marginally stable on the shooting of the infinitesimal mass. Now, if we have some finite, the minimum mass, let's say minimum mass is equal to 1, then unless particle is at least twice of that mass, like 2 or 2.5, they cannot decay. In other words, if the mass is 1.5, they cannot decay into two black holes with the mass 1 because the energy conservation. So all the energy conservation with some minimum mass makes some complicated the stability. But the conclusion is that there exists some parameter range where black holes are unstable under fragmentation in dEGB gravity. But I will not go to the detail. And then let's move on to the cosmology. Here we are given the action here, and this one can be given to the lambda CDM model if we neglect the Gauss-Bonnet term and the scalar field. Now, so here, question is, what is the major implication of this to the cosmology? So to do that, we have to write down the Einstein equation and also scalar equation. So Einstein equation, the Hubble parameter square is given by this total energy density. And while this the Hubble parameter time derivative, or this is in terms of A, it's A double dot, so it's related to acceleration or deceleration. That will be given by in terms of total pressure and total energy density and also pressure. So that's the equation. But here, what we are writing here is that all in the equations, all the scalar or Gauss-Bonnet dependent terms, we are moving to the right-hand side and then treat them as some new kind of matter. So Gauss-Bonnet, so at the formal, this is not real matter. At the formal level, we have Gauss-Bonnet energy density, pressure, and etc. Then, what we can tell is that since it is a formal level, there is no reason why the density, energy density, or pressure be positive. It can be positive or negative. So it's as a matter, it's very strange because energy density can be even negative. That's very strange. And the pressure is negative. That's also very strange. So in a sense, in that interpretation, you may see that Gauss-Bonnet plays some role that is unexpected from the regular matter. And the next thing is, what is the boundary condition we will choose? So we are choosing the boundary condition at the Big Bang nucleosynthesis about 1 MeV. Then from there on, we'd like to solve early universe. The main idea is that once we are after the Big Bang nucleosynthesis, so many observations, so many models, so many data are available, so that if you are not, if you have a theory not consistent with the present Big Bang nucleosynthesis around that time, then it cannot explain the reality. So that is why we choose as a starting point boundary condition at the Big Bang nucleosynthesis and then solve above. So there, because of the three number of neutrino species, even if we add scalars, so scalar field, we just do not introduce any potential term because we are assuming that they are ultimately light or massless. So they should not carry too much energy. So this energy they can carry compared to the total energy cannot be too large. If it is more than that, that is inconsistent. Okay, that is the what would be different from the usual lambda CDM. Now, then what would be the solution? Solution is here written is somewhat complicated. But here, let me tell you here, usually the beyond Big Bang nucleosynthesis is a radiation dominating era in the lambda CDM. So we are putting only radiation in addition to the into the dEGB cosmology action. So there is some radiation. So if you just only leave this, then this is actually this represents that we are in the radiation dominating universe. But we have Gauss-Bonnet and the scalar field. So the role of Gauss-Bonnet can be positive or negative. So and usually they are always tracing the highest energy contribution. So they are canceling so that the total energy here written, this is the total energy, is actually much smaller than the radiation energy. So what we found is that if we go very, very high temperature, there is some there is some fixed point, and some of them is attractive, some of them are repulsive. So since we are backward solving, so that word may be somewhat confusing. But anyway, physically, the older solutions are so this is the, let's say, alpha and the gamma parameter. So once we fix the parameter and let it run, then in the high enough temperature, they will end up to some specific solution, which can be characterized in terms of the W, which is the total pressure divided by total energy density. So it is either, depending on the parameter range, -1/3 or 1, or so between 1 to 7.3. So it's a very somewhat different from the lambda CDM. So we may say that there appears new phase that we never had in lambda CDM. In the lambda CDM, we have usual radiation dominating and the matter dominating error. But here in the high enough temperature, new solution always appears represented by in terms of those W parameters. So here we just drew some W parameter. So they may be changing. It's a very somewhat not simple as lambda CDM, but anyway, they are changing in the intermediate temperature. But eventually, if we go high enough, they do not change and keep going constant. That's what we mean by attractor solution. So always there is some this kind of W equal 1, -1/3, and between 1 and 7.3, that kind of three different cases. We may call that if W is bigger than 1, W equal to 1 is the kination, because if you think about the free scalar field, pressure is T minus V, kinetic minus potential, but we are, and the energy density is T plus V. But if we are neglecting potential energy with a massless particle, then that's actually W equal to 1. That's a kination. So this is a super kination in that sense. So W equal 1 is the kination. And the W equal to -1/3, as you know, this is the boundary. If W is bigger than -1/3, it is a decelerating universe. If W equal to smaller than -1/3, like a -1, then it is the usual dark energy, with some cosmological constant. So there are such three types depending on the parameter range of this model. So if we have enough high temperature, as you can see here, is clearly they are in the so new phase. However, if the temperature is not high enough, still they are not reaching but more complicated in terms of W's. They are not at the asymptotic values. And so here is the analysis of the autonomous equations to really understand the fixed point by redefining x and y for their energy densities. And then everything becomes in the first order equation. Then by essentially the tangential this integration curve will give the solution flow. And for the critical point, we can analyze whether they are repulsive or attractive. But those things, I will not do that. These curves means once we have initial condition, in such XYZ space, how it flows as temperature is going up higher and higher temperature. But I will not go to such detail. It's very technical. Okay, then let's move on to some examples of the cosmology. Essentially, if you have any event, you may always think what would be the difference in the dEGB cosmology compared to the lambda CDM. For example, we just studied inflation and found that the e-folding time becoming shorter, and also there is some blue shifted spectrum is possible, and there are many interesting properties, but I will not go there detail. But also, let me only briefly mention that if we have a WIMP particle, then weakly interacting particle will be in the very high temperature. They are in thermal equilibrium, but at some stage they cannot catch up the expansion speed. Then they are freezing, and afterwards, expansion is too fast to the, compared to the interaction rate. Then there is no more interaction. They are out of thermal equilibrium. If they decouple earlier, then the remnant of the present time will be, the dark matter will be more. If they are decoupling later, the remnant will be smaller. Now, the main idea is that this right-hand side, the Hubble parameter, will be quite different from lambda CDM. So in other words, it will make this decoupling time different, freezing time different, so that remnant will be different. So as a result, we can get from the fact that we have not seen dark matter annihilation. If dark matter was very much, then they should annihilate it and give us some signal in terms of gamma photon or E plus E minus like that. But since we have not yet had some convincing such evidence, there cannot be too much remnant, and it will just give some constraint on the dEGB model. And due to the time, so maybe better for me to move rather than keep explaining this phenomena. So as a final example, let me just mention you gravitational wave radiation. Here I just mentioned you the WIMP particle, and let's think about some gravitational wave in the new phase. So in the lambda CDM picture, there is no new phase. Keep every above some the t equal is always only the radiation dominating phase, radiation phase. So in the very high temperature, everything. So we have charged all the fundamental particles are dissociated, like into the quarks and the gluons and electrons and neutrinos like that. So it's a charged particle plasma, relativistic, in thermal equilibrium. Then they will emit gravitational wave stochastically. So the mechanism, you may think in terms of the electromagnetism. If you are heating up some, let's say, so that very hot temperature in thermal equilibrium, then at the microscopic level, the charged particles are moving, so it's ionized or recombined or percolated or annihilation or whatever. There will be such microscopic the current the fluctuation, and they are actually related to the emission of the electromagnetic wave. And essentially, the black body radiation should be also on the microscopic level like that. So similarly, this kind of thermal fluctuation of this particle, the plasma soup, they will give some fluctuation in the moment of inertia. So as a result, there can be some stochastic gravitational wave emission or absorptions and like that. So then, what would be that gravitational wave? As we know, once gravitational wave is produced, they are essentially thermally decoupled, and so that without any further interaction, they should arrive to us. So according to these gentlemen, they analyzed the energy density carried by such fractional wave radiation produced in a very high temperature. Here, I mean, so just they consider in the very high temperature only, of course. So then, the result is also very complicated integration. There is an integrand and the integration. Then it boils down to the fact that essentially the highest temperature will dominate. So in other words, let's say, so in the integrand, eta is an important thing, and there is some peak and some frequencies and etc. etc. So this eta will be picked at 3.92, and if we convert that to the present time frequency, this frequency, then it comes to the 74 gigahertz. So extremely high frequency, considering that gravitational wave frequency that we are used to is order of 1 hertz or 100 hertz or like that in the Kagra or Lisa, I'm sorry, LIGO, all the frequencies are order of 10 or 100 or order of 1 essentially. And in the like Lisa or Taiji or in such Tianqin, in such projects, they are even looking for the millihertz. Considering that this is extremely high frequency, and essentially so everything boils down to this temperature dependence. So how should we understand this one? So let's just talk about in terms of lambda CDM model. Then, if we are considering the radiation dominating era, this is electroweak, the cosmological phase transition up to there, in this region, the highest temperature is at maybe we can go up to reheating temperature, let's say. So then, here, so assuming that we can just calculate the energy density. So as I will show next page, as we will see in the next page, it's a really tiny amount. So it's not be able to be observed. That's much smaller than the present technology bound. Now let's talk about some non-standard cosmology. So here, let's say since due to the Gauss-Bonnet term or many other reasons, let's say radiation dominant stops here, and there is something else phase in our the dEGB cosmology. That's the dEGB the cosmology we introduce that solution. But if we naively think about that, the previous results of this gravitational wave density, then since the maximum temperature is reduced to smaller one, then total energy density will be smaller. So we mentioned that in the lambda CDM, still it is below the observation, so much below the PBN bound, so we cannot observe it. But this is even much lower. However, this is very simple thing, and so no consideration of the evolution of the Hubble parameters, etc. But if we just consider all those things into consideration, then in the dEGB scenario, that's we get some different results. So to just tell the final result is that For example, gravitational wave, usually the red color is what we expect from the lambda CDM. But the blue color is the what we get in the dEGB cosmology. So in this case, for example, gamma equal to 5 and alpha is I don't know, or it's not somewhere hidden here. In that parameter range, in the dEGB, there is even much smaller than this lambda CDM results. However, in some parameter range, so this is okay. So this is the region, the alpha is a negative. So this region corresponds to this region. Horizontal axis is alpha, vertical axis is gamma. So this region is completely ruled out in the sense that it's hopeless to observe any signal. It's much, much smaller than lambda CDM signal. However, if you look at this part, actually there is an enhancement so that it may be, so there is a BBN bound. Depending on how you really put it, it may be close to the BBN bound or even more. If it is even more, then since there's an inconsistent, we should have seen something. But anyway, so that's the BBN. So very can be enhanced very much like 10 to the minus 18 to the 10 to the minus 7, so like a 10 to the 10 factors enhancement. That can happen in this model. So metastable one I will mention. So through that, what we can here, what I'd like to show is that actually so far, all the observation of the gravitational wave were based on this hertz, 100 hertz or something, and people are interested in the lower frequencies. However, the one that we showed just a minute, the few transparencies before, is that there can be extremely high frequency gravitational wave signal from that source. And lambda CDM case, it is hopeless, too small. However, in some theories such as dEGB, that can be enhanced and observed. To observe it, if we have a high frequency, then wavelength is gigahertz is some few 10 centimeters or something. So it's a really tabletop size equipment. If it is really low frequency, 10 to the 2 or something, it's a million or more than million kilometers or long. So that's why we have to have a few kilometers arm length and let it be oscillating many, many times. So that it is comparable to the wavelength size or something. So really very large scale equipment for this low frequency. However, in the high frequency, actually it does not cost much. It's a really cheap tabletop experiment. The only thing is that so far people haven't had any motivation to search. So it will be very nice. I'll be very happy to see some experimentalists develop such equipment to test. If they do not see any signal, that means it will constrain the dEGB cosmology parameters. If they see something, maybe dEGB may be actually the thing beyond the right directional theory, beyond Einstein gravity theory. Okay, that's what I wanted to say. So as a summary, we try to just give a motivation that it's a really right time, it's a good time to go to study the theory beyond Einstein theory. And one of the simplest way would be the introducing higher curvature terms. In the four-dimension case, that is nothing but the dEGB gravity theory. And we start so introduce you briefly the black hole properties, and also in the dEGB cosmology, there are many other aspects which I have not discussed at all. Even though it was written in the my PPT file, the essential thing is a new phase occurring. So we introduce you something about the WIMP physics and also gravitational waves, and so it will be very drastically different from the lambda CDM, and maybe really worthwhile to pay attention to high frequency gravitational wave too also. Okay, thank you very much.
Thank you for the talk. Are there any questions? Yeah, Jutta?
Yeah, thank you very much for this nice and interesting talk. I'd like to come back to the first part of your talk, of course, the black holes. I mean, we're always faced with this gap that we have the minimum mass and we cannot go below. And there are various suggestions. And maybe you can elaborate a bit on this concept you mentioned, these solitron stars, why there would be these solitron stars and what properties they might have.
Okay, so if I understood correctly, I think that's a very interesting and a good question. I myself think about this kind of solitonic star. In other words, what I have in mind is that it's a very compact object, but no horizon. However, in the asymptotic observer, many things may be very similar to the black holes, including the emission of the gravitational waves or such things. And what bothers me most is Hawking radiation, especially. So according to Hawking, so black hole will be evaporating all the energy into the particles, and by that process losing mass, and eventually so vanishes, nothing left, right? However, in this case, if we have if we start from some heavier mass and keep losing energy through the Hawking radiation, and if we are close to the solitonic star, what is happening there? Then it will be stopping, and the soliton star will be remaining as the just a dark candidate of the dark matter and such thing. I guess I have not worked on that, even though I just thought about that. So I guess if it would be interesting if somebody can make a real progress.
Yes, I fully agree. This is a really fascinating point about this type of theory. And there's so much speculation in relation with Hawking temperature also. Maybe the whole, it's just not a stationary black hole anymore. It's something that is really time dependent or whatever. And I fully agree with you. Having some progress in this direction would be wonderful. Thank you.
Okay, thank you for the nice question.
Any other questions? maybe I can ask a question. You spoke about black hole fragmentation, and I wonder when a black hole fragments, basically I would expect it to be quite unstable. How high is the probability that the resulting black holes are in the end stable?
Okay, so here I only simply argued based on the entropy, whether the single black hole entropy is bigger or smaller. So I just comparing the single black hole entropy to the double black hole entropy. However, the transition probability is something else. E to the minus, we have e to the minus s, right? So there must be some potential barrier and the tunneling process. So even though in principle, it may be in the energy configuration, it looks like unstable. If the potential wall is very high, then of course, essentially we should say that it is practically stable rather than unstable, right? So that kind of tunneling amplitude and eventually tunneling the probability, I have not done any calculation. So only with that calculation, I guess this my statement for the instability should be correct. This one is only the halfway done, even less than half. Critical thing should be the really tunneling process calculation.
Thank you. Are there other questions? If not, thank you very much again for the talk. And I
Okay,
stop
thank
the
you.
recording.